When we talk about tessellations, we'll talk about a little translation and freeze patterns. All right. Glide reflection is when you take it, you slide it and flip it. So you can look at some of these to see if they have glide reflection. Translational symmetry just means you're translating it's the same pattern over and over and over again. So when you're looking at some of these patterns, you can assume they continue in both directions. So if you're looking at these music notes, they have translational symmetry because it's the same thing over and over again. They do not have glide reflection. I would have to flip them, so that would just be translation. Here, this would be translational because all patterns have translational, but this would be glide reflection. You take it, you flip, you take it, you flip, and so on and so forth. Okay? So translational, glide reflection. Translational is the same thing over and over again. Glide reflection is where you take it and you flip it. Okay. When you tessellate or tile the plane, you can't have any gaps or overlaps. So the measures of the angles that meet at each vertex need to add up to 360. So 360, 360, 360. So they all meet at the vertex. They assume extend indefinitely in either direction. Okay? A regular tessellation is formed by congruent regular polygons. So a regular tessellation means that one regular shape tiles the plane. A semi-regular shape tessellation means that more than one regular shapes has to tessellate the plane. If it's not regular, then it can't be regular or semi-regular. The shapes have to be regular. What makes a shape regular? Same side, same angle. So like equilateral triangles, squares, regular hexagons, so on and so forth. Okay? So when we're looking at these, this would be a regular tessellation. Those are all equilateral triangles tessellating the plane. This would be a semi-regular tessellation made up of squares, triangles, or just squares and triangles, excuse me, more than one regular shape. Okay? Every vertex has 2 squares and 3 triangles in this order. Square, triangle, square, triangle, triangle. So you got to put your pencil on the vertex, and to be semi-regular, it has to be the same at each vertex. So square, triangle, triangle, square, triangle. Square, triangle, it's the same pattern at each vertex. When it's regular, that's easy because they're all the same shape. Okay? So, tessellation is regular, semi-regular, or neither. All right. Those aren't regular shapes. That's easy. Neither. Those are all triangles, equilateral triangles. Regular. All right. This one. At each vertex, is it the same? Hexagon, square, triangle, square. Hexagon, square, triangle, square. Yes, I don't see anywhere you can assume. So this would be semi-regular. Okay? Has to be all regular shapes in the same pattern. Okay? Here we've got all hexagons. So that's regular. You're good there. All right. This one's where we get tricked up a little bit. Hexagons and triangles, you're good. But if I put my pencil here, it's triangle, triangle, hexagon, hexagon. If I put my pencil here, it's triangle, hexagon, triangle, hexagon. It's not the same at each vertex, so it's neither. Okay? Then this one kind of looks like that one, but a little different. Every vertex is triangle, hexagon, triangle, hexagon. Triangle, hexagon, triangle, hexagon. So that would be semi-regular. Okay? But to be either regular or semi-regular, you got to be a regular shape first. Then the pattern has to be the same. All right? Hope that makes sense to you. All right. Determine whether given regular polygons can be used to form a tessellation. If so, draw the tessellation. You guys don't have to draw any tessellations for me, but you do have to explain whether or not it will work. So remember, to figure out the angle of a polygon, we take n minus 2 times 180 divided by n. Okay? So, we know this is a triangle, that's 60. So, we want to see at each angle, does it go evenly into 360? Well, 60 goes into 360 6 times. Nice and neat, evenly. That is why this will tile the plane with no gaps or overlaps. Okay? So you got to kind of use this formula to figure these out. So this is a triangle. This is 60. 1, 2, 3, 4, 5. That's a pentagon, regular pentagon. So 5 minus 2 is 3 times 180 is 540. Divided by 5 is 108. So each of these is 108. Well, is there any way to get 108 and 60 to add up to go into 360? You can try on your calculator. You can take 360 divided by 108, and you can see that it's not a nice, neat number. Pentagons will not tile the plane. They can't do it. The angle's too weird. There's going to be gaps and overlaps. Okay? Let's try that again. Okay? What about here? What about a hexagon? Just by itself. Well, six-sided. 6 minus 2 is 180. Or minus 2 times 4, 180, I think is 720. Divided by 6 is 120. Let me double check that again. Yeah. So each one of these is 120. Well, 120 goes into 360 3 times. So the hexagon works. There's 3 hexagons at each vertex. 120 goes evenly into 360. Okay? What about hexagons and squares? Well, we know a hexagon is 120 and a square is 90. Is there any way to get those to add up? Well, 120 plus 120 is 240 plus 90 is 330. What about 90, 90? That's 180 plus 120 is 300. Doesn't work. What shape ties those two together? A triangle. Okay? Really the only regular shapes that can tile the plane that are answers to these problems are a combination of, or by themselves, regular triangles, squares, and regular hexagons. Okay?